So today we're going to learn about the remainder theorem. So to start off with, we're going to do a little warm-up exercise here, and we're going to practice doing synthetic division. So if we're dividing x squared plus 5x plus 7 by x minus 2, remember we always start by writing the coefficients of our dividend up here at the top. So we have a 1, a 5, and a 7. Okay, and then we take our divisor, figure out what would make it 0, 2, and that goes there. And then we add down and multiply to get up. So multiplying by 2 this time. Add down, multiply up, add down. Okay. And that gets us a quotient and a remainder. So you'll notice the remainder is 21, and the quotient will have a constant of 7 and an x term of 1. So 1x plus 7 is the quotient, and the remainder is 21. Okay. So take a minute, do the exact same thing for example B, and hopefully you got a quotient of x minus 7 and a remainder of 20. Okay, so if you look down here, they've set the dividend as f at x, and they're asking you to find f at 2. So if we plug 2 into our function f, we would get 4 plus 10 plus 7. That would be 21. Okay, and over here they've once again declared the dividend to be called f at x, and this time they're asking us to find f at negative 3. So that would be 9 plus 12 minus 1. That would give us 20. Okay, and what you hopefully should notice here is that the remainder ended up being exactly what we calculated when we found f at 2. Or in this case, the remainder ended up being exactly what we calculated when we found f at negative 3. And that 2 and that negative 3 aren't random, because it's the same number that appears on the left side of our synthetic division. So in other words, when we took that number and we plugged it into our dividend, it actually spit out the remainder. Okay, same thing here. When we took our negative 3 and we plugged it in to the dividend, we got back the remainder. So this is a way that allows us to figure out what the remainder is without having to do the division. Okay, and sometimes we just care about what the remainder is, or even if there is a remainder. So let's do one more example of this. Okay, so once again, we're going to do the synthetic division. A 1 would have made the divisor 0. We have a 1, a negative 4, a 5, and a 4. And we're going to quickly do synthetic division. So bring down the 1, multiply by 1, add, multiply by 1, add, multiply by 1, add. Because now we realize we're only looking at the remainder, we have a remainder of 6. Okay, and if we plugged in 1 into our dividend, we would get 1 minus 4 plus 5 plus 4, which is 6. So once again, we could have found the remainder by just taking the number that we would have used for synthetic division and plugging it into the dividend. And that's actually what the remainder theorem says. Okay, and this here in yellow is the official statement of the remainder theorem. It says that if f at x is divided by x minus p, then the remainder is f at p. Okay, so in other words, you can take p, plug it into f, and you will get back your remainder. For the proof of this, all we need to do is we need to take this general form, right? Dividend f at x equals our divisor x minus p times some quotient q of x plus some remainder r. And then the remainder theorem tells us that if we plug p into this function, we should get back our remainder. So let's give it a try. So everywhere there's an x, we're just going to replace it with a p. So here we have p minus p times q of p plus r. And p minus p is, of course, 0 times q of p plus r. And it doesn't matter what q of p is, because when we multiply it by 0, it would go away. And sure enough, we are just left with the remainder. So by plugging in p into our expression, you do get back the remainder, and that is the proof of that. So here's our first example. It's asking us to find the remainder when this cubic is divided by x plus 2. So I'm going to call that cubic f at x, and technically I should do a proper let statement. And to find the remainder, all I'm going to do is I'm going to find f at negative 2. So I'm just going to plug a negative 2 in everywhere. And if I work this out, then I will get the remainder. So I have negative 8 plus 16 plus 6 minus 5, which ends up being 9. So the remainder is 9. And we could have, of course, also found the remainder by actually doing the division. Here's our next example. We have a quadratic that has a k as the coefficient of x, and it's saying that when it's divided by x minus 2, the remainder is 3. Okay, so once again, I'm going to call this f at x just so that we can refer to it. So if f at x is divided by x minus 2, the remainder is 3. So what that really means is it means that f evaluated at 2 will equal 3. Right? Because when we evaluate it at the number that would have made our divisor 0, we always get the remainder. That's what the remainder theorem tells us. So I'm just going to take the function that I have for f, and I'm going to plug a 2 in everywhere. So I'm going to get 2 squared plus k times 2 minus 17, and it's going to equal 3. And now I just have to solve this. So I have 4 minus 17, that's 2k minus 13 equals 3. And if we isolate here for k, we would get that k equals 8. So that means that the trinomial here would actually be x squared plus 8x minus 17. Okay, but there we're only asking us for the k value. And that is the remainder theorem. Okay, next you guys will be looking at the factor theorem.